Today we're going to spend some time talking about a Mitutoyo coordinate measurement machine, model number B706. On this particular device we're going to measure an aluminum block with various holes and features. This is, as I said, a manual machine. It's not as fancy as your DCCMs, which is direct computer controlled measurement devices, but I think you'll enjoy this. And this will expose you a little bit to how a manual CMM works. In your laboratory handout, you'll notice there's a good information blog here on the objective of the laboratory, as well as an introduction to CMMs. This manual machine will measure the aluminum block that you see mounted right here, and we have various features that we will measure in the video. We probably won't measure all of them, but at least you'll get an exposure to how a CMM works. You also notice in the inspection procedure there's a way in which to turn on and utilize the equipment, and each button on the keyboard has a special feature or function for calibration, measurement of the part, as well as how to output the dimensional readings taken, and then of course how to shut down the machine. Over here you'll notice that the CMM has a kind of an older interface as far as a DOS-based system, with the printer, the main desktop, CMM control box, and then of course a flat screen monitor and a keyboard. One thing I wanted to point out to you was the way in which the keyboard is constructed. You'll notice that a normal keyboard usually has the A, S, D, F, G, and all that on the top. Well, on this keyboard we have different features for measurement that are listed, and the order in which you have to use each one is detailed within the laboratory manual. To save time in this video, the printing element has been set, parameters set at inches, and the projection onto the part is on the XY plane. You'll also notice that we're at level number 2, lower right hand part of the monitor screen, Cartesian degree, minute, second, and fixture number 1, ASCII off, and various things you can see on the screen there. The calibration of the stylus on the calibration sphere requires that we press calibration button. We select calibration micro or macro. Standard, of course, is 1 in this case. And then we are encouraged to move the probe around the calibration stylus ball. And I'll move the camera around here so you can watch that. Now we will turn on the probe. And then we'll catch the second point that's called out on the monitor screen. Then we'll get point 3. And then we'll go for point 4. And you'll notice that on the screen we have calibrated the stylus. Last element, D of 0.1965, which is actually the probe. Before we get too far on measurement of parts, we must establish our coordinate system. Pressing the XYZ button and then selecting pattern coordinates as you see on the screen, and then we're going to go to plane, line, line. Now you'll notice on the screen it is flashing. I'll get a little closer here for you. It's asking me to establish a plane. On the part, I will do just that. Now it's asking for, that was plane A, now it's plane B. Now it's plane C. You watched the computer screen earlier. This is how I established the plane A. As you can see, it's a little harder to do this manually than as you can probably surmise on a computer controlled type device. And here are the results of our workpiece coordinate system, WCS, for the aluminum part. For the first procedure, we are told to position the probe and circle, and then the Z-axis should be center of the bore. You'll also notice on the control module that you have a non-lit green LED on INT. This allows me to position it without unfortunately adding the wrong points at the wrong time. Only when that turns green can I add the actual points. Now I'm going to position this in circle A, which is right here. Leave it, and then I'm going to press this button on the keyboard. And you'll notice on the screen that it's asking me to hit 3 points inside the circle, which I shall do now. I will turn on the green light, and I will attempt to get these points. And then I'll lift it back out of the hole. And then when we come over here, you'll notice on the screen we're giving various values on X, Y, Z, the diameter, and the change of X, Y, and Z. Please notice the diameter, 0.4725 inches. That is the diameter of that circle. I have already measured circle B. Now I'm going to try to measure the line, first step, for the C dimension, which is this step here to the opposite side. If you'll look at your print, you'll know what I'm talking about. Now, this is a little bit more tricky than it looks. I've turned off my control box, and I'm positioning the probe along this area here. Now I'm going to press this button to measure the line. The first step for the C dimension. I've already pressed the left button, and you'll notice that it is flashing against that surface. Turn on the control box, hit the point. Next, you'll notice that X is 2.355. That is the dimension that we measured. Moving ahead in our laboratory procedure, you'll notice that we have a dimension here called G, where we measure from the C plane to the center line of the A hole, called the G dimension. Since we've measured the A and the plane, we can obtain the G dimension. To save time, of course, we did not measure all these other dimensions, but when we go through this procedure, it will pull up in memory the different numbers that we need to calculate G. As you can see, we press that button. We look for YZ plane, and the memory element in this case is A6, the 6, and center. For the purpose of this video, the memory element for the A hole became A10 instead of A6, but that's okay. I already typed that in, hit enter. Now I'm going to choose center, and then we get the actual dimension of 0.5938. As you'll see here, it becomes A15 as opposed to a procedure which it calls for memory A12, because we're off a little bit because of the setup of the machine. But as you can see, it does the same function. It measures the distance. Because of time constraints and the need to get you through this laboratory for manual CMM, you'll notice on the paper that various features and dimensions, widths, diameters, you name it, are being measured on this aluminum block. Within the manual CMM, as you measure each portion, you'll notice the different memory locations, A2 in this case. You have your base plane set for XY, projection on XY, A3 memory, and then we did an alignment. We measured the line, point intersection, then we switched to plane, line, line, and you'll notice the dimensions there. And then we did a projection onto the XY plane, last element. Mainly what I'm trying to get at is, as you measure each feature on the machine, you will have that dimension loaded into a memory element, and then when you're ready to find out what the actual dimension is, through a sequence of pressing buttons on the keyboard, you're able to determine what that dimension is, whether it be G, K, J, or E, whatever. Works very well on the manual machine.